Looks like I'll have to record this sick haul. Hey, let me throw 7 classic dice, and if a single number appears more than once, I'll buy you a drink. 3, 2, 1, and dang it, I accidentally tapped out of the window. Looks like we'll never know if I owe you one. Wait, you think I owe you one? Why? No one saw the same number appear twice, did they? No, don't worry. I'm not trying to gaslight you to avoid paying for a cheap drink. I was testing your math skills. You don't always need to see something for it to be proven true. You know what's cooler than a drink on a hot summer's day? Winning an Olympiad, a Math Olympiad in this case. Because I was testing you on knowledge on just that. Sometimes you can also prove by counting. I know you're probably rolling your eyes because you don't need to calculate something difficult for something that seems obvious. It doesn't require much calculation. Still, it is possible to prove more than numbers on dice with this. Anyways, want some skills? There's the rainbow, as they say, with their 5 colors. Wait, that can't be right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Well, I guess they are too short of the rainbow colors. Anyways, just because I don't want you to eat all of them, I'll allow you to eat one of each color, okay? Because you'll eat one of each, and there are 5 colors, you'll only eat 5 of them, right? So when you want to eat the most Skittles, you'll eat the ones of differing colors. If you like to see the glass half empty, you can also see you didn't eat any of the colors 2 times or more. That'd be the same as you saying, I ate 1 or less of each color. Therefore, if you eat one more Skittle on top of the 5 you already ate, you would have to eat from the colors you already ate, since there are no more colors left. In that case, you broke a promise and ate one of the colors twice or more. If you follow my order and eat only one for each color, you'll eat the most you could have. But if you eat one more, you'll guarantee that there will be a pair of Skittles of the same color. You could eat more and more, but that wouldn't fix the promise. Eating random wouldn't help, since you checked each color to make sure you ate the maximum. So interestingly, this last Skittle is guaranteed to make a pair of Skittles of the same color. So let's try this again, but with M&Ms, which have 6 unique colors. If I told you you can eat one of each color, you can eat at most what I said. That is 1 per color of 6 colors. 1 times 6 or 6. Again, if you were to eat a 7th M&M, you would certainly have a pair of the same color. 2 things I want to point out is that if you randomly take colored candy, the 7th one isn't the one that will create a pair of the same color, but is the one that guarantees it. I could torture myself by picking M&Ms to prove a significant difference between 6 and 7 M&Ms. Instead, I decided to torture my computer to simulate 1,000 of these random M&M pickings. After I wrote the horrible code, here's the result. So there's a border for each M&M color, and the computer picks one at random and counts the number of times that color appeared. If one color occurs twice, the computer puts the M&Ms away and tries again. This number is the percentage of all the tests containing a pair of the same color. The simulation continues and runs 1,000 more tests. Therefore, the chances of all the colors appearing only once are rare, but not impossible. Which apparently looks very similar to the percent of you guys that aren't subscribed. So consider changing that. I'll leave that to you. Unlike if we were to change the number of M&Ms taken from 6 to 7, where the code ran the same 1,000 tests and got none. Hope you enjoyed the hours of rendering on that one, because my computer sure didn't. Oh, there's a better way to prove this. No, there isn't. You're delusional. Back in the garbage you go. I swear to God, I didn't render for hours for there to be a simple proof. Sorry, I had to blow off some steam over there. So what did we just prove? If n items are placed into m containers, where n is larger than m, one container must hold more than the number of items it can have. In our candy scenario, the candy was the items and the containers were the colors of the candy. Oh, you think this is easy? Solve this then. Time's up, and let me show you how it's supposed to be done. Prove that having 100 whole numbers, one can choose 15 of them so that the difference of any two is divisible by 7. So the thing I didn't teach you yet is the fact that when dividing a number, having a remainder means a part of that number is preventing it from being perfectly divisible. You know that 14 is divisible by 7 without having decimal places. That means 14 is perfectly divisible by 7. If we were to add a number from 0 to 6, let's say 5, to 14, we get 19, which dividing by 7 will result in a decimal number. Therefore we say that 5 is the remainder of 19 when dividing by 7. You get 7 categories of numbers. Numbers that are divisible by 7, and those numbers that have a remainder of 1, 2, 3, 4, 5, and so on. We don't include a remainder of 7 because that's like being divisible by 7. What you don't know is that if you subtract numbers with the same remainder, their result will be divisible by 7. But on that someday later. That means the 15 numbers chosen need to have the same remainder. So we have 7 categories and 100 items split between them. But what about the part of there always being a group of 15 items that satisfy a certain condition? For 7 categories to hold 15 items, in one category we need to make sure that 100 is more than 14 times 7. Why 14? This is the number of items a category can hold before creating a group of 15 items that satisfy the condition. So is 100 truly bigger than 14 times 7? The answer is, in fact, yes, since 14 times 7 is 98, a little under 100, therefore satisfying the condition of there always existing 15 numbers that have the same remainder. Following our steps backward, we can see the question was in fact correct. 100 numbers is greater than the number of possible remainders times one less of the number needed to satisfy the group of 15 numbers within the same category, 7 times 14. That proves there are 15 numbers with the same remainder amongst each other. Having the same remainder after dividing by 7 proves that when you subtract any two of them, the number becomes divisible by 7. And that proves the question in the beginning. Don't believe me? Well, I made another simulation. This time I generated up to 100 random numbers from 1 to 1000 at a fast speed. And when I got 50 numbers with the same remainder, I stopped. Then the same simulation takes the 15 numbers, subtracts each possible number from one another and checks if its result is divisible by 7. If it is, the result gets highlighted in green. If not, it turns red. You see that there wasn't a single instance of that. Now I want you to confirm yourself by watching this simulation. And by doing the math yourself, you can see that in fact each number is really divisible by 7. So overall, this is everything I wanted to teach you about the pigeonhole principle. In a nutshell, if more pigeons than the capacity of all equal pigeonholes fly into them, there will be a pigeonhole that doesn't follow the capacity rule. To those who found this obvious, I hope you've come to appreciate the applications of such logic. And to those who heard about this principle the first time, I hope you learned something new. With that left off, there's still a lot for you to discover in math. Some of these discoveries I've discussed in my video about geometry and the path to finding formulas of area for multiple shapes. I leave you on your journey now. Bye.